So the primary valency is ionizable. Now what does that mean? So I have been using this complex a lot, but this is like the first complex that comes into my mind, so this is the first complex that I use in examples. So when I say that the primary valency is ionizable, not when I say, when Werner says that the primary valency is ionizable, he means that if you put it in water, this entire complex, then the ligands which satisfy the primary valency, they get ionized. That is, they dissociate from the entire complex, which leaves a 3 positive on this complex, because the overall charge still has to be 0, right? The overall charge has to be 0 on the right hand side, because the overall charge is 0 on the left hand side. So because it has to be 0 on the right hand side, so if there are 3 Cl negatives, means the charge here is 3 into minus 1, which is equal to minus 3. So on this complex the charge has to be plus 3. So this is what he means by the primary valency being ionizable, that is whatever valency is present outside, whatever ligands are present outside the complex are ionized when you put the complex in water. On the other hand, the secondary valency is non-ionizable. Take the same example. Put it in water. The primary valency gets ionized. But if you look at the secondary valency, it is still attached to cobalt. It is not getting ionized. It is not dissociating from cobalt. It is still there. It has retained its identity. So the secondary valency is non-ionizable, whereas the primary valency is ionizable. Now let's study about what the actual representation of Werner's compound is. How Werner said the compounds, the coordination compounds will be represented. So in order to know how the coordination compounds will be represented, you need to know first the primary valency of the coordination compound and the secondary valency. If we talk about this complex, then first of all we find the primary valency. Primary valency is CO will be X. So X, primary valency is the oxidation state. So find the oxidation state of cobalt. So X plus 6 times of NH3 plus 3 times chlorine will be equal to 0, because the charge on the overall complex is 0. So X plus 6 into 0 plus 3 into minus 1 is equal to 0, which gives you X is equal to plus 3. So the primary valency is plus 3 and it is satisfied by negative ligands, that is the chlorine is going to satisfy the primary valency. Now let's look at the secondary valency. What is the secondary valency of this complex? So secondary valency is the coordination number, so it's evident because there are 6 ammonia present within the coordination pair. So the secondary valency of cobalt is 6. Primary valency, remember, it was 3. For the same complex, the primary valency was 3. Now the secondary valency, according to conventions, the secondary valency, they are shown by solid lines. Primary valency is shown by dashed lines. Whenever you are trying to represent a compound using Werner's representation, first write the metal atom. Like first you will write the metal atom cobalt. Second, what you have to do is you have to satisfy the secondary valency, that is whatever secondary valency you can see, draw them using solid lines. So there are 6 secondary valencies, so 6 solid lines as in the image on my left. So there are 6 solid lines and the secondary valency is satisfied by NH3. So just write NH3 after all the 6 solid lines. Now primary valency is 3 and the primary valency is satisfied by 3 chlorines. So there is 3 primary valency and the primary valency is shown by dashed lines. And just write chlorine at the end of it. So this is Werner's representation of CONH3 whole 6 and Cl3. Now let's move on to a next similar complex and see if its representation changes or not. Okay, so in this complex we have 2 chlorines outside, 1 chlorine is inside, 1 ammonia is less. Now let's see what the structure, how we got this structure which is written on the left hand bottom corner. First of all, again you have to find the primary valency or the oxidation state. So take cobalt as X plus 5 into NH3 plus Cl plus 2 into Cl. So X plus 0 minus 1 plus 2 into minus 1 is equal to 0. So X is equal to plus 3. Here also the primary valency is coming out to be 3. And again they are satisfied by negative ligands, which is chlorine in this case. Now let's see about the secondary valency. So the secondary valency is again the coordination number. In this case also it is evident that the coordination number of cobalt is 6. Cn means the short form of coordination number. So coordination number of cobalt is 6 because there are 5 ammonias and 1 chlorine. So coordination number is 6, that means the secondary valency is 6. And the primary valency was 3. So the primary valency and the secondary valency is equal to what we got for our previous complex. So let's see how the representation of this complex changes. First of all, you're going to write the cobalt or the metal atom at the center and draw the solid lines for the secondary valency. So there are 6 secondary valencies, so 6 solid lines. And at the end of the solid lines you have 5 NH3s and there is 1 Cl. So the secondary valency is satisfied by 5 ammonia ligands and 1 chlorine ligand. Now there is 3 primary valency, so just write, draw 3 dashed lines. Okay, so you're going to draw 3 dashed lines, but the thing is only 2 chlorines are present outside, but there are 3 primary valencies, you have to satisfy them. So what you will do is only this chlorine which is present within the brackets, that is going to satisfy the primary as well as the secondary valency. So this chlorine satisfies the primary valency and it satisfies the secondary valency, but this is not ionizable because even though it satisfies the primary valency, it is still present within the coordination pair. Okay, so this is how the structure has changed even though the primary valency and the secondary valency was equal to our previous complex.